Welcome, everybody. The room, I'm told, is officially full, so we might as well get started. Nobody else can come in. So, welcome. My name is Jim Demmel. I'm the chair of the ECS department here at Berkeley. And on behalf of the department and our co-host, the Simons Institute for the Theory of Computing, I'm very happy to see you all here today. Today is the third in a series of talks in celebration of the 50th anniversary of the Computer Science Division at UC Berkeley, and most of all, a celebration of the 8 ACM Turing Award winners whose award-winning work was developed here at UC Berkeley. So you can see all of them up there. And in addition, this work was started, going back in history, back to the 1970s and the 1980s. But if you look at the entire history, Berkeley has more alumni who've won the Turing Award than any other school, 11 different students and faculty. And so our celebration of these accomplishments is a fitting complement to the 150th anniversary of the University of California, which is what we're celebrating this year. So that's the background. And today's speaker is Professor Dave Patterson. So Dave was a professor of computer science at UC Berkeley for 41 years, from 1976 to 2016. And he's now a professor of the graduate school, the fancy name we have for Emeriti, and a distinguished engineer at Google. He coined the term reduced instruction set computer, or RISC, in 1980 to describe an approach that was very different from the complex systems that were prevalent at the time. And RISC required a smaller set of simple general instructions for computing and requiring fewer transistors. So Dave later teamed up with his fellow computer scientist, John Hennessy at Stanford, who was doing similar research there. And together they published in 1990 a foundational textbook, Computer Architecture, a Quantitative Approach. And that established an analytical and scientific framework for engineers to evaluate microprocessor design, to make it really quantitative. And this text is credited with shifting the emphasis from raw performance power to an approach that takes energy usage into account, heat dissipation, and off-chip communication, because those are all the things that are most expensive. And Dave has won over 35 awards in his career, and the one we're here to celebrate is the one that Dave and John Hennessy won, the IEEE, well, they won the IEEE von Neumann Medal in 1990 for this work, and most recently the ACM's Alfred Turing Award, which is the most important award in all of computer science. So let us welcome Dave Patterson.
Thanks, Jim. Yeah, so I'm still stunned when Oosterhout told me, because I found out about the Turing Award and I couldn't tell anybody about it for about a month, and so I went and visited him and I told him, I have something special to tell you, and I came a couple days in advance, and I told him he won the Turing Award, and he said, "Oh, phew, I thought that was it. It was that or you had cancer." and then he told me this story. Because if you look at Turing Awards, there's all kinds of ways they count it, because I guess people argue about it. And one of them is even they count it where you did your undergraduate degree, all kinds of things. Where are you now? Where are the Turing alumni now? One of them is did you visit this school? That we had people visit it. I don't know how much credit you should get for visitors. But John said, well, what matters is not where the people are now or where they used to be, it's where was the research done. And by that measure, we leave everybody in the dust, right? There's 7 Turing Awards so far. It's about a 20 or 30 year delay. So far, 7 Turing Awards have been done at Berkeley, and that's what this celebrates. But and I was explaining it to somebody else and how to put it in perspective. That's MIT, Stanford, together, Berkeley, same number, right? So it's an astounding fact, and it's just part of our humble nature that we haven't quite figured it out on our own. All right, so what I'm going to do is give you the history of computer architecture, where I've spent several decades. We're going to do that in 10 minutes. Current challenges, or 10 or 15 minutes, this is a longer one, and then opportunities in the future. I think the lessons from 40 years of computer architecture are, first of all, that software people give ideas to hardware people that inspire them, and that when you raise the software-hardware interface, that allows innovation below it. And then finally, What's unusual about computer architecture is it's tied to this industry. So, you know, in other fields, they'll argue which is better. In our fields, we argue like that at conferences, but then companies go spend billions of dollars to try our ideas out, and the marketplace sorts that all out for them. And I'll give you some stories about that. So let's go back almost 60 years ago. IBM had this big problem. They had 4 independent lines of computers. Now, the way that software talks to hardware, there's a vocabulary, and what we call that vocabulary the instruction set, and the words of the vocabulary the instructions. So they had 4 independent vocabularies. So the software stacks were different. The market niches were different. Scientific, big and small, business, real time. They even had their I/O systems were really different. So IBM engineers thought what they should do is see if they could invent one of these vocabularies, one instruction set, to unify these 4 different parts of the companies together. Well, then and now, the problem isn't kind of what's called the data path. You can think of that, the brawn, the thing that does the multiplies and the adds. It's the brain, it's the control. That's the hard part of design. So how are they going to convince these 4 independent kind of companies inside of IBM to all do the same thing? They needed a technique. So they decided to go to Maurice Wilkes, computing pioneer, second person to win the Turing Award. And he had an idea how to make it easier to do the brain of computers. He said, let's specify control as a 2D matrix. The columns of the matrix will be control lines, and the rows will be the words that we program the control lines. We'll call that a micro instruction, and the programming of that, we'll call it microprogramming. So he wrote this paper, but people really didn't pick it up. IBM decided to bet that they could do one instruction set for the 4 different divisions using microprogramming. And in April 1964, they made the biggest announcement in the history of the company. And they announced many different models. Here's 4 of them there. But they varied, the data path, the brawn part varied by a factor of 8, the clock speeds by almost a factor of 4, and the costs by about a factor of 6. And so, you know, IBM bet the company on this idea, and they won that bet. IBM dominated the computing industry for the next several decades. And to this day, almost 60 years later, IBM mainframe computers are still a $10 billion a year business for IBM. And who was the person who led this 360-year effort? That was Fred Brooks, you know, another Turing Award winner, and which got it from part for the 360. Now, that was, you know, barely using individual transistors. We started getting to integrated circuits. And what that meant now was before, those matrices, which were implemented as read-only memories, programmed at time of manufacture, could now, and not because it was cheaper and faster, but now the way this was built, this technology, they could use plain old memory technology, RAM memory technology. And because Moore's law applies to integrated circuits, the memories got bigger. So what that meant is you could have bigger microprograms, and what that meant, you could have more complicated instruction sets. So you can think of what's in that control store, that array, as an interpreter for this instruction set. And the shining example of that is the VAX computer, and it had a much larger control store than the past. Since it was made out of alterable memory, an idea came out. So this is, you know, like the brain of the computer. How about if you let the computer modify its own brain? And that was called Writable Control Store. So this let microprogramming meant that it was not just inside of companies, but even academics could do that. And I worked on one of these computers as I was a PhD student. In fact, that's my PhD thesis, is about how to get bugs out of microprograms. Surely the most famous writable control store computer is the Xerox Alto that came in '73. It was the first computer to have a graphical user interface and the first computer to be connected together by Ethernet. Who did that computer? And Microcoded is this. This was done by Chuck Thacker, one of our alumni who won the Turing Award, the 3rd computer architect to win the Turing Award. And that Alto is the machine that he built that is the forerunner of all the computing that we have today. From the Alto came the Macintosh and came the Windows PC, and that was pioneered there, and it was a writable control store computer. Let's go to Silicon Valley and the microprocessor industry. Now, the microprocessor industry was fueled by this MOS technology, but at the time, what chips they sold were 8-bit microprocessors, so only work on data 8 bits at a time. They weren't really good at architecture. They were good at manufacturing and designing chips. So they just kind of copied what the big guys did. They copied what IBM and DEC did on computers. And when they were going to innovate, people programmed these small computers at the lowest level of programming, very tedious level called assembly language programming. And they would justify a new instruction by figuring out some way to use it and have notes, and they go back and forth. So that was kind of the state-of-the-art microprocessors. So Gordon Moore of Moore's Law fame, a Berkeley alumnus, was clearly one of our greatest visionaries. He, at the time, as the founder of Intel, when they had this 8080 microprocessor, thought the next vocabulary we do, the next instruction set we do is going to last for the lifetime of the company. So he hired a bunch of PhDs in computer science, sent them up to Portland, Oregon, away from Silicon Valley to invent the next great instruction set. This was called eventually the IAPX 432. It's one of the most ambitious computer projects ever, and certainly of the 1970s. It started in 1975. The ideas, this is when microprocessor 8-bit, they decided to do 32-bit computer. Not only that, have this idea for security reasons to put capabilities, kind of like keys, into the address space. It was object-oriented, and they even wrote their brand new operating system in Ada, so incredibly ambitious. There's a cost to ambitious. The cost is being late. So the people in Portland had to fly down to Santa Clara and tell Gordon Moore, oh, thanks for sending us up here. By the way, it's not going to be done in time. So Intel and Gordon Moore, and they had some performance problems as well. Intel and Gordon Moore started an emergency project. They had to have a 16-bit microprocessor, and they gave them 52 weeks to do it. That meant design the instruction set, build the chip, get it ready to go out the door, make it work. So that gave them 3 whole weeks to design the instruction set. So 3 weeks, the next great, this instruction set to fill the gap. And it was finished on time, to their credit, and it was made available, but not too much fanfare. There wasn't much excitement. The really good news was over in Florida, IBM was deciding to compete with Apple to make their own personal computer, the IBM PC, as it'd be called. And they needed a microprocessor, so they went with the 8086 because another one that was much like the 360 that was more elegant, this Motorola 68000, was late, so they couldn't use it. So they announced it. Now, it wasn't that big a deal when IBM picked it, because IBM thought over the next 5 years they'd only sell 250,000 of these computers, which isn't that many chips from a microprocessor. But they were wrong. They got it completely wrong. It was 100 million. So it was 100 million. So suddenly, this emergency placement 8086 was a brilliant idea. Because the way software is shipped in the instructions of the vocabulary, so-called binary, in that it's in numbers. And so to be compatible with the PC industry, you had to use software for the 86. So suddenly, the 8086, this emergency replacement, had this incredibly bright future. And the 432 that was supposed to invent the future with the great ideas came out several years later and kind of went out of business quickly. Let's bring in what's happening, analyzing these microcoded interpreters. Well, this is a picture of John Koch, another Turing Award winner in computer architecture and in compilers. What changed from the microprocessors is this idea that we mentioned from history of when you raise the level of abstraction, you can innovate. What changed was, thanks to Unix operating system, our alumnus Turing Award winner Ken Thompson created the Unix operating system and showed that you could even write an operating system in a high-level language. So there's no excuse to write an assembly language anymore if you can write operating systems in it. So now what mattered isn't how some clever person could use these instructions. What mattered was, what's the output of the compiler? So Koch thought he'd do an experiment. And what he decided to do, that's the mini computer that he built. What he decided to do was use his compiler technology only on the subset of the IBM instructions, the simple instructions. What would happen if it just used the simple instructions there and ignored the complicated ones? Well, it ran up to 3 times faster than using the whole instruction set. Well, that's a surprising result. Then a couple of DEC engineers with that VAX mini computer they measured it, and what did they find? First of all, the surprise was it took 10 of these micro instructions on average per complicated instruction, and that was like twice as many as they had guessed. They didn't think it would be that bad. And moreover, a lot of that microcode was never used. It's 20% of the instructions were 60% of the code, and they were almost never used. So that called into questions. Now I kind of surprisingly took a sabbatical while I was assistant professor here because I knew about how to make microcode, get bugs out of microcode, and they invited me there for leave. And so while I was there, I helped them, and it gave me some time to reflect about my Berkeley experience. And I came back and said, well, what's so special about this microcode? You know, why do we have 2 levels of programming? Is that really necessary? So I came back, and then Carlos Acana and I started working on the RISC project. So here's the ideas that are easy to explain today. So instead of having the fast, small memory to have this microcode interpreter, instead we transform that into a cache. Now a cache is just a small, fast buffer that has recent instructions, because the way software works, you're probably going to use it again. So now it'll have what the programmer wants to execute. So that's kind of like compiling versus interpreting. It's a very simple instruction set. It's as simple as micro instructions. It's just not quite as wide. It made pipelining easier. Pipelining is like when you assemble a car a piece at a time. The throughput is much faster when you do pipelining than if you did assemble the car one at a time. So that made it go faster. And by the way, the complicated instructions, you know, weren't used that often anyway, so what were you losing? And then there was a breakthrough in what's called register allocation from some IBM people, where they made it easier for the compiler to use those registers, where it's at the heart of the RISC architecture, so that made it even more efficient. So this is where, you know, the universities come into the picture. So Carlo Acana and I led the effort for RISC-1, and we did it through a series of courses here, 4 graduate courses. I tied it to the deadlines so that we'd have real deadlines. And that was the first RISC chip. In fact, there's a plaque in Soda Hall on the 3rd floor from IEEE commemorating the first RISC chip. It worked, but it wasn't fantastic, so 2 grad students led primarily with Carlo did RISC-2, and at the same time, John Hennessy did the MIPS project at Stanford University. And there was this remarkable moment in time where these 2 chips were presented to the leading conference in integrated circuits in San Francisco. And at the end of each presentation, there was this murmur in the audience where they talked about it. And to me, still, it was this I remember the remarkable moment in time when it was clear that a handful of grad students at Berkeley or Stanford could build a microprocessor that was arguably better than what industry could build. Faster, cheaper, more efficient. So what an amazing event. RISC was very controversial. It was heretical. The idea was you should have a vocabulary that was rich and high level so it matched software. All kinds of bad things happened in the world of software because it was too low a level. So we had a hard time convincing people of that. But this formula helps explain it. Basically, the first part of the formula is the instructions per program. Since we had simple instructions, you needed more instructions per program to execute. But the second part of the formula is about how long did the instructions take. So it turned out the complex instructions took like 5 or 6 times as long as the simple instructions. So 25% more, but 5 times faster, so the net effect was about a factor of 4 better. So that took a while to do that. Now the fact that there was a formula here, the guy that designs, was unusual that time in computer architecture. No textbooks had any formulas in it. So John Hennessy and I decided, you know, we didn't like the textbooks, and we were going to try and bring out a book that captured that, and that's the book that Jim talked about. And the subtitle of A Quantitative Approach was a real kind of pointed approach to what's been done in the past. And in some ways, you can think of us inspired by Don Knuth's Volume 1 on algorithms, which is a more quantitative approach to algorithm design, and this is a kind of an architecture successor to that. Okay, what happened? So wrapping up the you know, kind of 2/3 of the history here. So Intel didn't take this lying down. They had this complicated microcoded instruction set. To their credit, they figured out a way to get 500 engineers on one project. And the first thing that they did was build hardware that would translate the complicated instructions on the fly into their own internal RISC instructions. What a remarkable thing to do. And then, once they were in RISC instructions, any good ideas that the RISC people did, they could do. So they had much better semiconductor technology than anybody else in the world. So they could build chips that would translate, take advantage of RISC ideas. And because they were in PCs, which have very low margins, the computers were very cheap. So they became as fast, they were cheap, and that meant they were very successful, hundreds of millions per year, and eventually that instruction set, by about 2000, it dominated not only the desktop, but servers as well. So that's at the peak of the PC era. The iPhone started the post-PC era in 2007, and the world changed. First of all, instead of buying chips from Intel to put in your computer, you're building your own chip, a so-called SoC for system on a chip, that goes in every cell phone. So every cell phone has a system on a chip. And now you want designs from many different companies to put in the chip that you're designing. That's, the designs are called intellectual property, or IP. And now what do they care about for cell phones, right? They care about die area, because that's cost. They care about energy, because you have a limited battery, as much as performance. So now the original things that the RISC microprocessors did of fewer transistors and more efficient matter a lot in this space. So the number of chips that in this space are remarkable, Internet of Things, cell phones, cars, microwaves, stuff like that, 20 billion a year, 20 billion 32-bit, 64-bit processors last year, and 99% of those are RISC. So this is, again, the marketplace at the end of the post-PC era, x86 ones, but today it's RISC that's winning that. Okay, what's next in history? What's next in history is something that was going to replace both RISC and CISC, and it's called very long instruction word. And the idea was simply that instead of having one operation typically per instruction, you'd have a lot of them, say 6 of them. And then whose job was it to kind of, it's like a checkerboard where you put all the instructions in and they had to be put in the right spot. That was the compiler's job, and the VLIW advocates believed compilers were ready for that challenge. At the time, it was time for Intel to come up with a new architecture. Its address spaces, it's called. 32 bits was starting to run out because memories were getting bigger, so they needed to go to 64-bit. So they decided to bet on VLIW. They gave it a new name, EPIC, for explicitly parallel, but it's basically that. The chip was called the Itanium. Not only did Intel decide to do that, they decided to join forces with Hewlett-Packard. So 2 of the most powerful companies in Silicon Valley are joining forces on what they said is going to replace RISC and CISC. AMD had the rights to do the x86 architecture from Intel, but Intel wasn't thrilled about that, and so they didn't let them have the rights to Itanium. So AMD was forced to just make a 64-bit version of the x86, kind of like the Booby Prize here. Now, once HP and Intel said, look, the people with the best technology in a serious computer company said, this is the future of computing, a bunch of companies just said, okay, if you say so, and they just abandoned whatever they were doing and pledged to use it, to use the Itanium. Alas, it was an epic failure. So as Don Knuth, our Turing Award colleague at Stanford said, the Itanium approach was supposed to be so terrific until the compilers proved to be impossible to write. So this bet that the compilers could handle it proved to be a false bet. Again, like I said, that's how we settle things, billions of dollars, put it in the marketplace, see what happens. First of all, there were very long instructions, so they were bigger, so that meant the instruction caches didn't work well. Secondly, for some types of programs, the branches are easy, but for the ones that most people use, the branching is very hard, and so they couldn't figure out how to schedule that in the compiler. And then cache misses were also a problem. So after all the fanfare for years about the Itanium was the future, pundits, and they were several years late too, the pundits started noticing it and made fun of them. And so instead of the Itanium, they rechristened it the Itanic. And so that within a few years, billions of dollars, it sank into the cold Atlantic Ocean and never to be heard from again. The good news for the VLIW advocates is there are these weaknesses that I talked about. There are fields that don't have these weaknesses. There's, digital signal processing has small programs. The code side doesn't matter. They don't have caches, and the branches are easier. So VLIW has found a home in some places. All right, so that's the history. That's, I guess 15 minutes of the history of computing. What's the challenges today? Moore's law, this brilliant, amazing projection that lasted for 50 years of exponential growth He said doubling every year the number of transistors in 1965. He amended it to 1975. This is the 1975 version of it. But you see that we're off by a factor of 15. No, if it's exponential, it can't go on forever because then, it's all the atoms in the universe. So he said it's not going to last forever, but forever being delayed. And he said that in 2003, and it lasted about another 10 years or so. As you can see, it's starting to fall off, and today it's way off. Today it's off by a factor of 15. So we are officially in the post-Moore's Law era. Now, when I tell young people this, they say, of course, we're in the Moore's Law era. The people who are older say, we've heard this before, so they don't believe me. But this is it. We are in the post-Moore's Law era. All right, a lesser known fact, and let me just say, my colleague Bill will remind me to explain this. What is Moore's Law? Moore's Law is not physics. It's not a law of physics. It's an investment strategy, right? It's a kind of a business model that if you make this investment, they will come. And so there have been tremendous investments, but they're just kind of running out of atoms, right? They just can't get the processing to keep shrinking at affordable rates. So recently, Intel, the so-called 10 nanometer, is a couple of years late. So instead of leading the world by 2 years, they are now maybe behind. Another thing, Global Foundries announced they're going to give up. They're not going to try 7 nanometers. So we're seeing the end of this. A lesser known law or observations, just as important almost, is Bob Dennard, the inventor of the one transistor DRAM that makes the memory technology we all use, observed this remarkable thing as the feature size gets smaller, so we can pack more transistors into a square millimeter of silicon. We dropped the threshold voltage, so the actual power density remained the same no matter how many transistors were there. I mean, otherwise, this question, well, how could you keep doubling the transistors? Won't the chip get hot? Well, we lowered the threshold voltage, so it would stay constant. And for a long time, it was flat, and that was so-called Dennard scaling. As things got getting smaller and running out of atoms, what happened is we keep shrinking the threshold voltage, it would leak power. And it would leak it a lot, not just a linear model. So what we see is around 2012-14, after being relatively flat for a moment, it shoots way up. So now power or energy is the limit more than area. So end of Moore's Law, end of Dennard scaling. And kind of the end of the line of processor performance. So for those young people in the room, there was a day when you would throw your perfectly good working computer away because your friend's computer was like 3 times as fast as yours, and it was like 2 years newer, and so yours was just a piece of junk, and you threw it away and you needed a new one. So that was the heyday of when performance would double every 18 months. With the end of Dennard scaling, that we couldn't do fast single processors anymore, so we had to switch to multi-core. There's this law from Gene Amdahl that says when you do things parallel, there's a serial piece that'll limit how fast you go. And then, shockingly, and this is the first figure of our textbook over 6 editions that were upgraded. In the last year, it only improved 3%. So single program performance improved 3%, double every 20 years. So especially the older programmers are used to kind of sitting in their chairs waiting for their programs to go faster. And so that they can keep making it more and more complicated and use it because, the hardware people will just make it go fast, so it's okay. That, if you're going to be sitting in your chair, you're going to have to sit there a long time. It is over. So I'm officially telling you that if you're going to use general purpose computers, it's not going to get any better. Or you won't even be able to measure it. So it'll be like the television community or something like that. So I've given the talk a couple times. A common question is what about quantum computing? I've read about quantum computing. So it's true that this is getting serious investigation. Big companies are spending real money on it. And the physics, math, and theory results are just beautiful. Phenomenal results. But this is not going to be you're not going to have a quantum computer in your pocket. Okay, this is like big science. It stops working if a truck rolls by. They have these big pieces of equipment, and it decoheres very quickly. So the quantum singularity is like, when will a quantum computer actually compute something faster than a general purpose traditional computer? They may become maybe a toy program in the next 5 years. Will it be 10 years before it does something better than a computer? It's going to be a number like that. So we need to do something we're going to have some other idea for clients. And even for the data center, we need something at least for the next decade. And that's not all the bad news. What about security? So computer people have been trying to make things go faster without you knowing about it by guessing what's going to happen next. That's called speculation. And we thought, it doesn't matter. As long as we go faster, everybody's going to be happy. So sneaky people figured out that by watching how you guess, they can learn information. Basically, if you're guessing based on a secret, they can reverse engineer that. And remarkably, you could leak information at 10,000 bits per second, which is a big one. And the one that was in the newspaper, Spectre, isn't the last one. Kind of every month there's a new vulnerability that's announced. And it's really not it's not a software bug, it's a hardware bug. We have to rethink what it means in computer architecture to hide information from timing attacks. So it's a big challenge. Okay, so this looks pretty bad, right? Moore's law, which we've counted on for 50 years, is over. Dennard scaling is dead. Processor performance isn't any good. And by the way, you're building hardware that leaks information like a sieve. All right. So what's our guiding principle? Well, we can't change the direction of the wind, so we're going to have to adjust the sails. Okay. So how are we going to adjust the sails? There's software-centric. So these wonderful modern scripting languages are fantastic things to teach and are very productive, but they don't run efficiently, and I'll quantify that for you. And then the hardware side, Hennessy and I believe if only path left is domain-specific architectures. General-purpose computers are not going to get any better. The only thing left is domain-specific. And domain-specific means they'll do that domain incredibly well, but the other domains they won't. And then the good news is that they kind of can be combined together. You can do domain-specific languages that, along with domain-specific architectures. And an example of that is our colleague Jonathan Regan-Kelly did this Halide language, which was invented to make it better for people to do a graphical image analysis. That he did it for the graphics people, but it raised the abstraction to let us innovate underneath it. How slow is Python? How slow is Python? So this is a study that Charles Leigerson at MIT did. Let's do a simple operation to quantify it. So first of all, we're going to write matrix multiply in Python. Only thing we're going to do is rewrite it in C. 50 times faster, rewrite it in C. Think of how many generations of hardware that is. Yeah, Hennessy was a compiler guy, and if for C++ programs, if you could get a factor of 2, you'd be a hero, right? This is a 50, just going from Python to C. Now, these things have multiple cores on them. All microprocessors have multiple cores. Let's rewrite the code, because compilers can't figure this out. It's too hard for compilers to figure out from C code where the loops are. We'll manually figure out where the loops are, and we can get another factor of 7. Now, a key part of microprocessors today is the memory hierarchy. These caches are talking about. So caches try and guess the way they work, but if you are very careful and lay it out to make the caches work better, you can get another factor of 20. And then finally, at the very lowest levels, Intel has what are called kind of basically vector instructions that can issue up to 16 32-bit operations per clock cycle if you can figure out how to use those instructions. So if you do that, you get another factor of 9. So how slow is Python? 63,000 times. So part of the reason John and I did this talk is to inspire people of problems to work on. There are Turing Awards waiting to be picked up. If you could make programs go 1,000 times faster, you would blow everybody away in the compiler community, and it looks like that potential is there. Factors of 1,000. How many generations of Moore's law would it take just to go 63,000 times faster? Okay. Now, what about domain-specific architectures? The idea is, they tailor to the domain and they throw out the stuff that they don't need. There's this phrase, application-specific integrated circuit. It sounds like it only does one thing. These things aren't that. They're using that so-called technology. There's still software. Software is a good idea, and software tailors it. Now, Hennessy and I did our book all about demystifying computer architecture to make it quantitative, right? So it's not magic that this happens. We understand what it is. To handle parallelism, there's two ways to do it. There's this vector approach, SIMD approach, one instruction at a time, lots of data. That's more restricted. It doesn't do as many things. But when it works a lot better compared to the classic MIMD multiprocessor one, much more efficient. Similarly, the VLIW I talked about earlier, when it works, it's very efficient compared to these speculative things that have these bugs in it that I talked about. So if your domain works, it works fine. So that can be explained to speed up. The memory bandwidth, I showed you the story with Python. So caches work great until they don't, right? So it's guessing what you want predictively. If you know what you want to do exactly in software, you can do it much more efficiently. And then finally, you don't necessarily need the same arithmetic precision for some of these applications that you could use for general purpose computing. So you don't need 64-bit floating point numbers. You could maybe even get away with small integers. So you multiply this together and there's big factors. And then finally, the great news for architects are these domain-specific languages, because you could always invent a wacko architecture, but how are you going to get software on it? Now that people are writing things that are important in languages that have higher level of abstraction, it's easier for you to map that into these domain-specific architectures. What field should we help? Here's a field where the number of papers grows with Moore's law. What field should we help? So that field is machine learning. Double the number of papers every 2 years. And when I last checked on arXiv, if you want to keep up, you have to read 50 papers a day. 50 papers a day to keep up with ML, machine learning on arXiv. And this is 2018, so it's even more. And if you design computers, the worst person you can meet and say, I think computers are fast enough. Wait, you hate that guy. What you want is somebody who says, I can't get my work done. Like, give me everything you got. So this is a field that has that. So that's Moore's law, if it was improving at Moore's law on a log scale. For the people at the very edge doing the training in machine learning, what do? They go up a factor of 10 every year. So that's their appetite. They could use, if you could improve to factor 10 a year, they can put it for use. So these are people architects kind of love here. So what's an example of this? This is from the last month's issue of Communication of the ACM on the cover. It's TPU version 1, a domain-specific architecture of deep neural networks. Here's the package, and then this was the cluster of these, 64 of these that was used for the AlphaGo competition. And this is actually not kind of what usually academics do and architects do, is they write a paper about this thing that they could build someday and it might work, right? This is the other way. It's been in production since 2015. If you use Google, you've been using TPUs to do some of the work. What's it look like inside is that it has this matrix multiply unit, which remarkably has 64,000 multiply accumulate units, 64,000. So how many is that? Compared to a traditional CPU, that's like 100 times as many as a traditional microprocessor, and 25 times as many as a GPU. So when you multiply 64,000 every single clock cycle times the clock rate, that's 90 tera operations per second. And this is something that was deployed in 2015. How well does it work? Well, compared to a GPU, it's about a factor of 30 better in operations per watt. And remember, energy at the end of Dennard scaling, energy performance per watt is a good measure, and then 80 times better than the CPU. Now, the way we evaluated that was using production applications, which is a nice thing to do. It's important applications, but we can't share those applications with everybody else. So the good news is we and Berkeley and Stanford and several other companies are trying to do a machine learning benchmark suite. For CPUs, the spec benchmark suite really brought everybody together, and they competed fairly and rapidly accelerated. Part of that doubling every 18 months was because we agreed on the benchmarks and could innovate and see what better. I think the same thing will happen for mlperf.org. The results are supposed to be out next month, so this will be a historic point. At some time, we'll see fair benchmarks for all these competing ideas, which I'll talk to you about. And Google announced that in May 2016. They have an event in May, and the following year they announced TPU version 2. That's what this looks like. This is for training. You can put 256 of these together, and this is like 20 feet long by 6 feet high. And that's the peak performance is 11.5 petaflops. This is for 16 and 32-bit floating point operations. That was May 2017. The following year, announced the TPU v3. This is liquid cooled, so it's so hot that you can't use air cooling. And this is a much bigger pod, and its peak performance is greater than 100 petaflops. So what do these numbers mean? So there's Jim, my introducer, is involved in a benchmark competition where they run the top 500 supercomputers in the world. They use bigger floating point, but they measure it in flops. And so using that type 500 list, the 16th fastest computer has a peak petaflops of basically 11, and the 4th fastest is about 100 petaflops. Now, it's not, this is the peak, so the question is, what fraction of the peak do we deliver? But you're writing programs basically in high-level systems like PyTorch or TensorFlow and running them on these supercomputers at extraordinary rates. And Google's not going to just build one of each of these, right? They're going to build a lot of those. So, if you believe this metric, it'll be 16 through N are this one, and I guess 3 through M are this one, and then this one is after it. And that's kind of one pace a year. So it's a very exciting time in computer architecture that's happening. And people are making all these different bets. Google is typically doing one kind of big core with these big multiplier arrays and software-controlled memory. NVIDIA, what's commonly perceived as the strongest one in machine learning, has many cores, many threads, many registers. Microsoft is making a completely different bet. They're betting on field programmable gate arrays where they can tailor this flexible hardware to the application. And then Intel's making all the bets. It's like a person that comes to the horse race and he wins every time because he bets on all the horses, right? So they bought Altera, which is what Microsoft FPGA. They bought Nirvana and NVIDIA Mobileye to do custom chips, and they're and they're improving their cores. And by the way, there are also 45 startup companies who are doing hardware for machine learning. A couple of years ago, a bunch of faculty in this room were saying, how can we ever get venture capitalists to invest in hardware startups, right? That problem is now solved. And second, what's interesting historically is in the past with general purpose computing, any idea you came up with had to work for general purpose computing. So the VLIW was kind of an interesting idea. Would it work for general purpose computing? The answer was no. But there's lots of other ideas. There's asynchronous computing. There's an idea called wafer scale computing, where you, instead of chopping it up into pieces and reassemble it, you compute using the wafer. All these ideas are being tried out with venture capital money right now, and we're going to learn about them through ML-Perf in the next year or two. So it's kind of a Cambrian explosion of architectures that are going on right now with venture funding. All right, so that was part one. Part two. It can inspire things. How come there's open source compilers and open source everything but architecture? How come? So this is where Berkeley comes in. It was time in 2010 to start doing an instruction set to design the chip designs efforts. The obvious ones were the ones that are obvious today, too, x86 and ARM, but it was impossible for two reasons. They were really complicated, so we would have driven the grad students away if we'd forced them to do it. And ARM and Intel wouldn't let us do it because it was proprietary. So Krista Sanovich, in the second row here, said, well, we should just do a 3-month project to do an instruction set. It's possible that I was skeptical about that, but he led it along with 2 star grad students, Andrew Waterman and Vincent Lee, and I gave sage advice, I guess. And it took them 4 years, but they built chips along the way, and it's a lot of work to do a real instruction set. Then what happened, right? Our colleagues in industry started complaining about us using RISC-V. That was okay, but we changed it from the fall semester to the spring semester. Okay, you guys complain about everything. why do you care with our instruction set why we change it from the fall to spring? And the answer to the question is, well, we wanted to find an instruction set that we could use. We didn't want to use proprietary ones, and so we found yours and started using it. So, aha! There's a demand for an open architecture. Well, that sounds like a cool idea. Let's try and make that happen. So what's different about RISC-V? It's really simple. It's hard for proprietary instruction sets to keep simple because partly it's marketing to add features and get, it's just hard for them to do that. We started 25 years later, so we could learn from the mistakes of our predecessors and not make them. That's easier to do. Like Monday morning quarterbacking. It's got a small standard one, from my historical perspective. It's pretty close to RISC-V, surprisingly. Without RISC-V without the mistakes, maybe. And lots of extensions, and it works either at the edge or the cloud. It's designed for both of that. It supports these domain-specific architectures that we just talked about, but the big difference is it's really a community design. It's free and open, and it's driven by a community, not by a company. So the companies involved, it started in 2015, 3 years into it. We've got about 200 companies. It's growing fast. Mentioning a few, these are 2 companies in China. It's pretty popular in China. Each of them are planning to use it, and they'll ship tens of millions of chips with RISC-V cores. NVIDIA announced that they're going to put it in every GPU, a microcontroller, so that'll be tens of millions of cores. And then Western Digital announced that they're going to do it and put RISC cores. They want to put processing near the data, and so they're going to ship like a billions of RISC microprocessors because that's how many disks they ship. And we just heard a story yesterday of a company that we'd never heard of called Kendrick that has a new microprocessor that's, I think the board has 2 RISC-V cores plus a neural network accelerator and 8 megabytes of RAM. And they're using open source technology, the software and the chips. And how much are they charging for this board? $3 to $4. So like, oh, Adreno, how can you afford an Adreno? Right? That's $60. Here, $3 or $4. So I think this could be like the path, just the beginning of this kind of explosion of what you can do with open technology. Usually what happens in computer architecture is you work hard to come up with an idea for an instruction set, and then you announce it, and all the software people will tell you how stupid you are. So what we're doing instead is getting the software people involved in the foundation before the extensions are completed. And so then when it's announced, then we've already incorporated that. And you can do it when things are open. And RISC-V isn't the only one. NVIDIA, to its credit, did an inference accelerator, kind of like the TPU V1. They made the whole thing open. The architecture, the instruction set, the software stack, and implementations. It's all available for people to download and use. And I think there's synergy between open architectures and security. Basically, the security community does not believe in security through obscurity. They like things to be open software and stuff like that. So they like an open architecture that they can see. It's also really simple, so that helps them if they want to do formal verification. And security is really hard. It's really embarrassing security is so bad. We need all the best minds working on it. Because it's open, everybody in the world can work on it. You don't have to have an Intel badge or an ARM badge to work on the architecture. Everybody can. And then there's particularly exciting opportunity right now because of the open RISC-V implementations and the open software stack, and because FPGAs allow you to run slow but fast enough to have real software, you can deploy your ideas on the internet subject to real-world attacks. You claim you have a security idea, put it out there, see if people break it or not, and then you'll learn from that. And then once you learn from that, you can iterate. And how fast do you iterate? It's an FPGA. You can iterate it every week. So we could see this acceleration improvement in security by using RISC-V and enhancements with real attackers and make a lot of progress as compared to, with using traditional chips, which kind of iterations every couple of years. So I think RISC-V is going to be that exemplar for that. Okay, so domain-specific languages and making Python go faster, open architectures. The last one is Agile development. So Agile development, which I learned about from co-teaching the software engineering class with Armando, is this breakthrough, right? Software projects crash and burn all the time. Is there a way to make them work better? And the idea is simply, instead of planning in years in advance, let's do it iteratively. Let's put it out there, get an early prototype, get feedback on it before you do the next step. And there's a thing called Scrum organization from rugby that means a small group, kind of a Scrum, 5 to 10 persons. And they do sprints where they work hard for 4 weeks and then take a break before they do the next iteration and get the feedback on it. So remarkably, advances in CAD design, like the chisel system here, allows that to happen. So we could do that in hardware. Now, that seems like you can't do that, really, because hardware takes a long time to build. But by looking at the different levels, you can. The first place to start is the simulator. If the simulator for the architecture, if you can do the experiments there, obviously that's software. You can do it in less than 4 weeks. But software is slow. If you want to run real software, billions of cycles, you can put it in a field programmable gate array, and that goes faster. Well, but you have to buy FPGAs. No, you don't. The FPGAs are in the cloud. Remarkably, you can go to the cloud and use FPGAs, and you don't even have to set up a lab to do that. Then, to do energy and layout, you need the layout. You need the chip design. You can generate that using commercial CAD tools. And then they're not done, so there's something that the Berkeley people call a tape-in to finish the design. Now, you could stop there. You could stop there because the CAD tools are pretty good. You could say, oh, I'm pretty sure the chip's going to be this big, it's going to use this much power, and it's going to be this fast. And you'd be pretty accurate. But that's like training for a marathon and then running 26 miles, and you can see the end over the, yeah, no, I'll stop here because, I'll probably would have finished in another 20 seconds, so I'll just stop here, right? But you miss all the reward for building chips. The one thing hardware people can do that software people can't, is we build physical things. You can show your parents, hey, I made this, right? And then you want to make sure it really does work. Maybe the CAD tools aren't quite right. So, but okay, only Berkeley can afford to do this. No, the chips, where we are in technology, for tiny, what are called test chips, 1 millimeter in the side, the list price to get 100 of these is $14,000. So anybody can afford to get chips now that they can design themselves. And so with the help of the RISC-V open technology, on one of these you could surely do a RISC-V core and one of the NVIDIA inference accelerators and do that chip. And maybe, who knows, maybe that's how that Kendrick thing did this. Big chips are expensive, but you can explore a lot of things with small chips. So Krista led this effort, and amazingly, they did 10 chips in 5 years. And I think in my career, I did, I guess, 4 chips in over 20 years or something like that, 4 or 5 chips in 20 years. He did 10 in less than 5 years with this Agile model. Okay, so wrapping up, the last slide before your questions. The lessons of software advances can inspire architecture innovations. That's what inspired Wilks to do the microcoded control, this translation versus interpretation, open architectures and implementations, and agile hardware development. Those are new things. We'll see how that works. Raising the interface, that let RISC happen, and now it's letting domain-specific architectures happen. The marketplace settles debates. The 432 and Titanium, the marketplace wasn't patient enough for them, and they lost, but successes can last for decades, like the 360, the PC, and ARM and RISC. The proprietary, right now the excitement is proprietary versus open going to work for hardware? We'll know in 5 or 10 years. And who's going to win the DSA sweepstakes? Which person has the best idea? We'll find out in a few years. But John and I think this is an incredibly exciting time to be in computer architecture, both in academia and in industry. And it's like when we were young, we think it's another golden age. All right. So, and I think I'm going to follow Silvio's model from last week, is I'll do questions for a while, and then if you want to stick around, I'll tell you my life story and my advice. Question?
Hi. Fantastic lecture. Thank you so much. Pushkar Apte from Citrus. Question, I'm a semiconductor guy, and one of the things that semiconductor guys are excited about is 3D chips. So I agree with you completely that in 2D, Moore's law is done, right? But if you go in the third dimension, particularly with really dense interconnections between processor and memory, people are proposing that where you would have the processor and memory elements really close to each other, distributed, new kinds of architectures. Is that a game changer, or is that incremental?
So yeah, the question is about is it a packaging technology or is it just semiconductor process? Okay, so right now, flash memory technology, so DRAM is running into a wall just like processors are running into a wall, but flash technology is continuing to go ahead, and it's doing it by multiple layers. So the question will be, well, yeah, we need ideas. So and so there's no bad ideas now. As far we need to desperately seek for new approaches. The challenge will be with more levels will be power, right? As you add more levels, the power density could get worse, right? And then even if we stop dead where we are at whatever it is, 16 nanometer technology, it's an amazing technology. You can manufacture millions of these, hundreds of millions of these things, and they all work, and they're pretty cheap and stuff like that. So the challenge for new technology is to achieve the same economics and reliability, and the big challenge for all chips today is power. So a question will be, as you add more layers, what happens to power? But there's no bad ideas to investigate right now. It's just that I suspect for the next 5 years, we're going to have to rely on computer architecture using current technologies before there's a replacement. But it'd be great if I was wrong.
Hello, this is a historical question, but it's kind of a Berkeley historical question. How would you place the small talk on a RISC effort going back then, vis-a-vis your characterization of domain-specific architectures, domain-specific languages, and the notion of virtual machine as maybe splitting a difference?
Yeah, so the question is about small talk on the RISC, which using revisionist history we call RISC-3. So I think the tie-in isn't so, I wouldn't say, that's not really I wouldn't call that domain-specific. It was kind of language-specific. But if you remember my Python slide with a factor of 63,000, I think an interesting question here is whether some of the small talk and a RISC ideas of some amount of hardware support for this object-oriented, dynamically typed language, plus compiler advances, a hardware-software co-design like we did for small talk on the RISC, will make a lot of sense today. Python is maybe the most popular programming language. I think almost every university teaches it the introductory one. It's probably going to get more popular. But what huge opportunities there. So I think there's a chance that people will look back at both the Spur project, RISC-4, and the small talk on RISC. Spur was trying to make Lisp go faster. SOAR was trying to make small talk, and some of those same ideas may make a comeback, which would be very cool. Oh, do you want to do the microphone, or I'll repeat it? All right. Okay, I'll repeat it. Or you go ahead. You can hand the microphone.
You were talking earlier about building better optimizations into higher level compiled and interpreted languages, but you were also mentioning that this hasn't really happened yet. And I was wondering, in your mind, like, what is holding these languages back from being able to be optimized on the level you were talking about?
Well, I don't think it's the languages that's holding it back. I think it's, we think it's a tremendous opportunity. I think I've talked to some people in compilers, and are people starting to work on this, and they're beginning to do this, but this is kind of a new thing, right? This is taking, because it's not clear how to do this. Besides Python, what about TensorFlow and PyTorch, right? Here, these are languages that have big, have arrays as building blocks. What's the right way to compile these things is a wide open question. So if you're young, this is a tremendous time, right? There's, what they told me when I got here to Berkeley was what we value is impact. We don't count papers, we count impact. I loved hearing that. I thought that was the coolest thing. And so that's what we try to do. So what you want as a researcher is to find a place that if you make an advance, it's going to have impact. And what I can tell you is if you you know, if Python's the most popular programming language in the world, and you can make it go 100 times faster, you're going to have a lot of friends. You know, the machine learning was up until the right? Lots of people are excited about the impact of machine learning on all of society. There's probably big opportunities to make that go a lot faster, and so it's a great time. There have been times in the past where, you know, kind of everything was on a steady course, and the compilers, industry knew what to do with compilers, and knew how to design microprocessors, and everything got better. That was kind of a boring time for researchers. You know, you should work on something else. But now, back-end systems architecture, hardware, software, co-design is a very compelling area with huge potential. So yeah, that would be my question. If I went to the compiler conference, I'd say, why aren't you guys working on this? Other questions? Where?
Great history, thank you. I sort of lost track between the death of the personal computer and the rebirth of the supercomputer. And of course, the cloud has changed everything. So where is computing actually going to be done? And
Great.
What is your view of the influence of the cloud?
Yeah, so you know, the cloud, there's a Berkeley version of the history where the cloud goes back to the Network of Workstations project that was done across the street, where, and some people here worked on it, where, you know, we showed that you could build powerful supercomputers out of off-the-shelf computers and connect them together, and that eventually, as they built bigger data centers, they figured out they could get economies of scale, and so now they have 50,000 computers in the cloud. So I think John and I think most people think, you know, it's the extremes. It's what the computer in your pocket, the computer in your car, the computer, you know, in your doorbell. The Internet of Things is one end, and the other end is the cloud. And the cloud is these warehouses of computers that are distributed all over the world and growing fast. When we did a cloud computing paper about a decade ago now about the view of cloud computing, and at the time a decade ago was like, oh, but 10 cents an hour for a computer, Amazon's losing money. So what happened? So now at Amazon, because cloud computing is such a big part of the business, they have to report it. So it's less than 10% of their income, but it's more than 70% of their profits. So, and they're growing by 50% a year. So the leading cloud supplier is growing by 50% per year and turning it into a very profitable company, just this one franchise. So everybody's working on it. So the cloud's going to be this giant piece of the future. The edge is going to be the other piece, and the rest of it is going to be gradually disappearing. So the laptops that all of us still keep buying, you know, that's shrinking every year. The PC sales drop about 8 or 10% a year, while phones and everything else explode around it. Okay, let me try and do, before I lose my audience, I'll do my history. All right. Okay, I have this. So I'm surprised I'm here. I think in some parallel universe, there's like thousands of opportunities, and this is one out of thousands. So I'll tell you my story. So I was the first of my family to graduate from college. I did well in math in high school, so I did math in college. I was a wrestler in high school and in college. But I had, you know, as the first one to graduate from college, you're thrilled to get a bachelor's degree. Graduate school isn't on the future. I knew of computers, but there were certainly no computers in my high school, and there was no computer science major, so I just took math. What happened was a math class was canceled at UCLA, so in the last quarter of my junior year, I took a computer class. And this is how primitive was this? This is punch cards, and you get your feedback once a day, and you know, you leave out a comma, that's one day's gone. And so it's just a miserable way to program. But it's kind of like video games 30 years ago. You could still get engaged, and it got me. Wow, the ideas in your head come alive in this program. This is it. I found what I wanted to do. So in my senior year, I took all the computer science classes in engineering and business that I could. I think 7 of my 10 courses were one of those. Accidental PhD student. So in my senior year, I took a computer science course, and I was working in a factory, and I just, you know, I said innocently after class was over, I did well as, boy, I'd sure rather do this than work in a factory to support myself going to college. And the young faculty member heard that, and on his own went and talked to a bunch of research projects and got me a job working on the project. And if he hadn't done that, there's no way I would have gone to grad school. But this was fun. I was in office with a bunch of grad students, and so I talked to my wife and said, how about I get a master's degree? That's pretty cost effective, right? 3 or 4 quarters. She said that was great. Well, then in my office, everybody else in the office was getting a PhD who assumed I was, so that seemed like a good idea. And so my wife said, well, if you think you can do it, why not? Okay. The bad news was we had 2 kids, and we're living on a 20-hour a week RA salary, and the grant ran out. So income goes to 0. That's not good. But a nearby company that made computers for airplanes, I got a part-time job, but it took a lot longer to graduate. Now, the good news for me being around this long is 7 years to get a PhD is not so bad anymore. But 40 years ago, 7 years for a PhD was a pretty long time. Accidental Berkeley professor. So I finally going to graduate to the shock of my in-laws that I'm finally going to get a PhD. And I started applying for jobs. And my wife, who came with me on one of the trips to Colorado, said, I just can't take this seriously because I think you're going to end up at Berkeley. I said, look, you don't understand. Berkeley's up here, UCLA's here. I'm a grad student. That's not going to happen. You do not understand how academics work. And then, but she had, and first of all, she grew up, she was born and raised in Albany, right next door, her parents made her move to Southern California when she was 11. She always wanted to come back. So she keeps asking me, what about Berkeley? What have you heard from Berkeley? No, I haven't heard from Berkeley. And so she finally forces me to call Berkeley as a grad student, call the chair of the department, and ask what happened to my application. And it was Elwin Berlekamp who was chair at the time. And so I call, and Elwin Berlekamp, by the way, is a famous mumbler. He's well known for mumbling. That's probably, if you look at the Wikipedia page, they'll probably mention mumbling. So I keep my finger in my ear, put the phone on, and I say, well, I've got a couple of offers, but Berkeley's the one place that if I heard from that I'd take seriously, and I hadn't heard from you. And so he says to me, well, Dave, you're in the top 10, but not the top 5. And I remember this tremendous relief that, that wasn't so bad, and hanging up the phone. So I learned later, he said that to anybody who called. And it was a polite way to say that, but he took my application out, and he said, And there was a faculty member who was going to Southern California, so he said he'd drop by UCLA and we talked, and hit it off, and so I got an interview and got a job pretty late in the season. The first project that I did with Carlos Acan and I and another faculty member who was leading the way, it was way too ambitious. We're gonna write an operating system and build our own chips, and by the way, we didn't have any research funding. So, which would have made it a little hard to pull off. So, 3 years into my assistant professorship, I took a leave of absence, went to DEC, and that's where I worked on microprogramming, and then I had time to reflect upon what works at the university, realized that there's no deadlines in universities. Maybe if I tied it to courses, there'd be deadlines, and we could do it that way, and came back, and we did the RISC stuff in a series of 4 courses. But then tenure wasn't easy. Carlos Acan was chair at the time. He thinks it wasn't so hard, but I remember it being hard, and that our field, our prime papers are conferences, which is unusual on campuses. What a weird thing. The conference papers usually don't count. It's journal papers, so I only had a couple of journal papers, and Carlo had to squeeze that through. And after that, things went better. So what's worked for me? My goal was to maximize personal happiness versus wealth. I think growing up in America, you think if you're wealthy, you're happy, right? So that's not necessary. Wealth and happiness aren't necessarily correlated. I think we have a president who might not be happy. But my goal was to be personally happy. I had some time to think about before I got up here, and I said I'm going to make family first. That was a really good idea. When you're assistant professor, you want to make everybody happy, so you say yes, so your family can be like 27th. So making it first so that and it's part of maximizing happiness. It's hard to be happy if you lose your family when you're there. Passion and courage. I like to think I'm a logical person, but I think I'm logical, but I'm also very passionate. So, and then kind of ironically, it doesn't make any sense, but the physical courage that comes from wrestling translates into intellectual courage. I mean, I feel like when something's not right, it's my personal job to stand up and say this isn't right, no matter what the political consequences of it are. So this passion and courage, we swing for the fences. You told me you want impact, we're going to try to have impact. We're not bunting for singles. But one of my colleagues recently passed away, Latvizada. Because of my passion and need to confront, he told me this saying: friends may come and go, but enemies accumulate. Right? So that was kind of a warning shot across my bow. And in my career, I know of 2 enemies. Now, as I look back, I feel pretty good about it. The person that tried to get hired here that I didn't support, based on what happens to that person's career, I'm really glad that career was someplace else. I think other people would be that. And then the person I really picked a fight with was the head of DARPA under George Bush administration, and he was just kind of defunded academics. And so I thought this was not just bad for Berkeley, bad for the country. And so Ed Blazowski and I confronted him, and he doesn't like that, being confronted. And I tried, talking to other universities nearby and elsewhere to join us. They didn't. He's a spiteful guy, so they didn't want to do that. So, but you know, if you pick a fight with somebody who everybody hates, you make a lot of friends. So, so yeah, but I call it enemies accumulate. Friends, oh yeah, we used to hang out together, but enemies never forget. So watch out. Winning as a team versus winning as an individual. For me, I did sports. I did wrestling, which is individual sport, but I had college and high school coaches who believed if we bonded as a team, we'd be more successful. So I just believe this in my DNA, that there's no losers on a winning team and no winners on a losing team. So I use sports, but I think anything that gets people together to collaborate to succeed would be a good analogy. So it can be theater, or it can be the symphony, or anything that groups of people can be a good guideline. But I believe in the team efforts. Seek out honest feedback and learn from it. I think I'm pretty good about that. If somebody really doesn't like my ideas, I send them the paper because they'll tell me frankly about it, and we try and take advantage of Silicon Valley to bring it out. So, and one other piece of advice besides enemies accumulate is watch out when somebody thinks they're the smartest person in the room. So my list is that one guy who I didn't get to come to Berkeley, the founders of Enron, the book's called The Smartest People in the Room. Both of them are convicted felons. The president of Ivy League College was fired. He thought he was the smartest person in the room. And I've actually got a relative of my ex-brother-in-law who thought he was the smart person in the room, and he's a felon, right? So what's the flaw, right? What's the flaw? I think they're actually smart. It's not that they're not smart. The problem is, if you think you're the smartest person in the room, then there's no reason to ask somebody else in the room for feedback on your ideas. So you just think all your ideas are great and go out with them. And I think that's what the downside is. So make sure you get, well, first, A, try to get feedback. And B, if you see somebody who says they're the smartest person in the room, run away. Okay. One big thing at a time. I still remember it was like God spoke to me one morning. It was a sunny morning, and I kind of woke up, and the saying that God spoke to me, it felt like, was, it's not how many projects you start, it's how many you finish. It was like I just woke up with that phrase in my mind. And it hit me, because in academia, it's very easy to volunteer for lots of things. And there's not a lot of follow-up in academia, you know? So you can end up with a lot of things. So once that hit me, it's how many things you finish, not how many you start. I tried to do one big thing per year. So when Hennessy and I wrote our book, that was the big thing I did that year. It's not like I didn't do anything else. I did lots of small things, but there was only one big thing a year. When I was chairman of the department, that was the big thing I did. When I was involved with the Tapia conference for underrepresented groups, that was the one big thing I did. But you know, it turns out that, you know, in an academic career that's decades, right? If you do one big thing a year, that's a lot of things, right? Especially if people don't finish most of the things they start. So I would seriously think about that. And then finally, I'm a natural born optimist. Actually, this is the penultimate slide. The next slide I've never showed anybody before, but I was at this Heidelberg forum where it's a bunch of Turing laureates, and he said what's on the next slide was the most valuable advice he got from me that whole week. So I'll tell you about that. So natural born optimist. I think, especially in research, but probably in a lot of things, it's better to err on optimism than pessimism. You know, will I make that bus? Well, let me try. You know, cautious optimism. How about, you know, we're going to try and build chips different from everybody in industry? Yeah, I think we can do it. I think a handful of students can beat industry, you know. Let's go for it. You know, it's research. It may not work, but why not? So I think optimism is better. And so my optimism story is when I was in high school, kind of the second girl I dated, we met out several times, and at that time it was to be, a couple, not date anybody else. We called that going steady. So I asked her if she would go steady. So her answer to me, she'd dated other guys, and she was only 16 and wasn't sure she wanted to, go steady at that young age. And so, but she liked me, so she said, "Well, Dave, I don't know how to say no." To me, as a logical person, optimist, I hugged her. Great. and so she thinks, okay, in a couple weeks I'll let him down. But we've been married 51 years now, so. And now, here's the secret. So when you've been married 51 years, actually when you get married 50 years, it's so rare that you can get, the president will send you congratulations and senators and stuff like that. So it's rare. So people always ask you, what's the secret? I will tell you the secret. 9 magic words. And you have to remember the words and say all of them, and there's no substitutions here. Now, if you're young and haven't been in a relationship for a long time, you're not going to get it. You're still in the honeymoon period. But if you've been beyond the honeymoon period, you're going to get it. The 9 magic words. I was wrong. You were right. I love you. And it's no, I was wrong, you're right, you're a jerk. You can't. That's how it works. So if you remember those words, it will actually help you have a long, happy married life like I had. All right, with that, I think I'll thank you and wrap it up.